Friends, welcome to the module 2, lecture 3 on the course Structural Health Monitoring. In this lecture, we are going to introduce static and vibration based health monitoring. Having said in the previous lectures that structural health monitoring has a primary objective with a basic concept that current health of a structure can be predicted, or I should say assessed, static or dynamic measurements. In simple terms, when a structure vibrates, under influence of any load, it may be ambient load or service load for which the structure is designed, then dynamic measurements can be used to characterize the structural condition at any instant of time. To do this, it is necessary to locate the damage if it is present in the system, so location of damage can be done by comparing the structural characteristics at pre and post damage conditions. By this logic, friends, it is mandatory to impose structural health monitoring in all structures of strategic importance. It is not necessary, in fact, it is a wrong concept that SHM should be carried out only when damage is perceived. As structural health can be estimated only by comparing the vibration characteristics before and after damage, even when the structure is healthy, one should impose structural health monitoring to obtain vibration characteristics before any perceived damage. Then one may ask me a question, if all structures are designed to cater to the varying dynamic characteristics, then why structural health monitoring is necessary when no damage occurs? That is a very interesting question. Friends, it is important to note that the dynamic characteristics vary significantly with the following: changes in loading pattern, because loading pattern will invoke redistribution, aging of the material, which we call material degradation, which can cause change in mass and change in stiffness, changes in support conditions with period of time, etc., can make the dynamic characteristics to be different from that of it is being designed. So, it is very important to periodically update the vibration characteristics of all structures, I should say, but at least for structures of strategic importance this is necessary, because only based on the pre-damaged state and comparing it with the damaged state, health of the structure can be assessed. Okay. So, let us talk about static based SHM. We all know that in structural health monitoring, the foremost step is damage identification. Damage identification can be also done through dead load distribution. Let us see how. The basic hypothesis behind this statement is that dead load of the structural system will get redistributed automatically when damage occurs in the system. Let us see then in that case what are the measurements required. Stress and strain developed due to lead loads are used as input to identify the damage. This is what we call as static load test. Let us consider a fixed beam as shown in the figure below. The beam is subjected to some loading pattern which is function of x, which is considered as q0, and x is measured positive towards the length of the member and y is measured positive towards upward. Let us call this end as A and this end as B. Let us say we have a moment applied here which is ma. The length of the member is L, and let us perceive that there is a damage at a distance A from the origin, that is from the left hand support. Let us say at section A, which is distance A from here, there is a damage in the beam. So, we call this as damaged zone. Therefore, this section will have EI undamaged and this section will also have EI undamaged, whereas this section will have EI damaged. Let us say it has got two reactions, RA and RB. So, let us say let the damage region B of span delta. So, this is delta and this is A. Okay. So, from the figure it is clear that the damage zone length is delta and damage location is A from the lead support. Let us say moment at any section XX in general is given by the following relationship. Mx is equal to plus Ra into x minus q x squared by 2, okay, plus Ma, where Ma is this, q is the downward load and Ra is this. Equation 1. Let Ei undamaged be the modulus of rigidity of the undamaged part and Ei damage be the modular rigidity of the damaged part. We already know that Ei d square y by dx square is equal to Mx. Integrating equation 2 once, we get Ei dy by dx will be equal to dmx by dx plus integration constant C1. Further integrating Ei into y will be d square mx by dx square plus C1 x plus C2, substituting for mx from the equation 1. Equation 1 is here, okay, substitute mx. So, Ei into y will be, okay, Ei dy by dx will be equal to Ra x squared by 2 minus q x cube by 6 plus Max plus C1. Ei is Ra x cube by 6 minus q x 4 by 24 plus Ma x square by 2 plus C1x plus C2. But there are different regions in the beam for which this equation should be separately written. Let us talk about region 0 less than x less than a. In that condition, Ei undamaged of y1, you can see here the equation, okay, Ei undamaged of y1 will be Ra x cube by 6 minus q x 4 by 24 plus Ma x square by 2 plus C1x plus C2. This is for 0 less than x less than a. Now, for region a less than x which is further less than A plus delta EI damaged, because that is the damaged region of y2 will be RA x cube by 6 minus q x 4 by 24 plus MA x squared by 2 plus C 3 x plus C 4. So, this is A less than x less than delta plus A. For region A plus delta less than x less than L, we can also write, again it is an undamaged region. So, undamaged will be VA x cube by 6 plus q x 4 minus q x 4 by 24 plus MA x squared by 2 plus C 5 x plus C 6. This is A plus delta less than x less than L. Let us see what are the boundary conditions. Let us replace this as RA. Let us see what are the boundary conditions to solve this equation. Y1 of 0 is 0, Y2 of 0 is 0 and Y3 of 0 is 0, Y3 of not 0, Y3 of L. This is the first set we have. The second set is Y1 of A will be also equal to Y2 of A, and Y2 of A plus delta will be Y3 of A plus delta, which imposes an additional condition. Ex is mxy by Ei undamaged, Ex is also equal to mxy by Ei damaged depending upon the region. Once this is set,